Hello and good afternoon to all of you. I hope all of you are doing well and all of you are in good health. In today's class, we will go through the pin description of 8086 microprocessor. As we have learned in the previous classes that 8086 microprocessor has in it 40 identifiable pins. These pins are sequenced with the help of a unique identification number starting from 1 to 40. We have also learned in the previous classes that 8086 operates in two different modes, namely max mode and minimum mode. Max mode refers to multiprocessor mode, whereas min mode refers to uniprocessor mode. If you closely observe this particular pin diagram, you will see that across some of the signals, the across some of the pins, the signal descriptions are different for max mode and min mode. You must have also observed that some of the signals in this pin diagram are barred and some are not. The non-barred signals are signals that are active high. That means these signals are considered high when it is at logic 1. Likewise, the barred signals are active low signals, and these signals are considered to be high when it's at logic 0. So that is the way how we distinguish active high and active low signals. Now, let us go through the signals that are there across the 40 pins of the 8086 microprocessor. So, at pin 1 you have VSS, at pin 2 you have AD14, 3, AD13, 4, AD12, 5, AD11, 6, AD10, 7, AD9, 8, AD8, 9, AD7, 10, AD6, 11, AD5, 12, AD3, 14, AD2, 15, AD1, 16, AD0. So pin number 2 to 16 is used in order to refer to AD0 to AD14. So these are address data multiplex lines. Now, pin 17 we have NMI, 18 is INTR, 19 is clock, and 20 is VSS. You'll see that in case of 8086 there are two ground pins. That is pin number 1 and pin number 20. So 21 is reset, 22 ready, 23 test. Now you'll see that uh, pin number sequenced from 24 to 31 has separate descriptions for max mode and min mode. So in case of max mode, 24 is QS1, 25 is QS0, 26 is S0, 27 is S1, 28 is S2, 29 is lock, 30 is request grant 1, 31 is request grant 0. Likewise, in case of min mode, 24 is INTA, 25 is ALE, 26 is DEN, 27 is DT oblique R, 28 is IO oblique M, 29 is WR, 30 is HLDA, 31 is hold. So these are the descriptions for pin number 24 to 31 for max mode and min mode. Now pin number 32 is RD, pin number 33 is MN oblique MX. 34 is BHE oblique S7, 35 is A19 S6, 36 is A18 S5, 37 is A17 S4, 38 is A16 S3, 39 is AD15 and 40 is VCC. Now let us go through the description of each of these signals. Now the first one is pin number 40, that is VCC. So at this point, at this pin, the external power supply of plus 5 volt is given to the microprocessor. So as we learned in the previous class that 8086 microprocessor has an operational voltage of 5 volt. Now pin number 1 and 20 is VSS. So these two pin acts as ground. This pin directs the extra current or energy of the microprocessor to the ground. Now we have pin 2 to 16 and 39 representing AD0 to AD15. Now AD0 to AD15, these are multiplexed address data lines. Now during the first clock cycle, it carries 16-bit address and after that it carries 16-bit data. That is AD0 to AD7 carries lower order data byte and AD8 to AD15 carries out the higher order data byte. But it takes place only in the latter half of the the machine cycle. Now we have A16 to A19, which also represents S3 to S6. Now these are multiplexed address status signals. In contrary to AD0 to AD15, which are multiplexed address data lines, A16 to A19 are multiplexed address status lines. So in case of memory operation, this pin acts as address bus and contains memory address of any particular instruction or data. However, in case of I/O operation, these pins are low, that shows the status of the processor. So these pins are used in order to so hold the address of the memory location from where the data or the instruction is to be fetched. However, in case of I/O operation, these pins are low, that shows the status of the microprocessor. Now, the signals S3 and S4 are explicitly used in order to represent which segment is currently being accessed by the microprocessor among the four subsegments that are present in it. So as we've already learned, that a typical program has four sections in it: a code segment, four segments in it, a code segment, extra segment, stack segment, and data segment. So S3 and S4 is basically used in order to represent which segment is currently being accessed by the microprocessor. Now let us see the possible combinations of S3 and S4 reflecting different segments. Now S3 and S4. So if S3 and S4 has both 0, then it refers to that it means that microprocessor is accessing extra segment. It with 0, 1, microprocessor is accessing stack segment, 1, 0, code segment, 1, 1, data segment. Now these are the significances of the status signal S3 and S4. Now let us try to understand the importance of the status signal S5. Now S5, whenever it is enabled, it shows the presence of interrupt in the microprocessor. So it serves as an interrupt flag. So S5, when enabled, shows the presence of an interrupt in the microprocessor. So it serves as an interrupt flag. Now let us try to understand the significance of S6. The signal at S6 shows that the status of the shows the or reflects the status of the bus master for the current operation. So this implies who is the bus master, whether 8086 microprocessor itself is the bus master or there is some other proefficient device that is acting as the bus master. So when S6 is 0, it implies that 8086 is the bus master or is having the control of the buses. Whereas if S6 is 1, it implies that there is some other proficient device acting as the bus master. Now, so these are the significances of S3, S4, S5, and S6. So S3 and S4 is used in order to indicate which section is currently or which segment is currently being used by the microprocessor. S5 is used in order to indicate interrupt, and S6 is used in order to indicate the bus master. Now the next signal that we have is BHE S7. So BHE is also known as bus I enable. So the combination of BHE signal and S7 shows the status information about existence of the data on the data bus. That is whether whether there is whether there is data in the data bus or not. So that is reflected by the bus I enable signal and S7. And also possible combinations of this would reflect whether the entire 16-bit of data is to be considered, or upper byte or the lower byte of the data is to be considered. So this is the importance of bus I enable and a status signal S7. So it informs about the existence of data on the data bus. Now likewise, you have another signal MN oblique MX bar. Now MN oblique MX bar is used in order to represent whether the microprocessor is operating in maximum mode or the minimum mode. So the status at this particular pin shows whether the processor is operating in minimum mode or maximum mode. So a signal 0 at this pin informs that 8086 is operating in maximum mode, that is multiprocessor mode, while Signal 0 shows that the microprocessor is operating under minimum mode or single processor mode. So we have learned about minimum mode and maximum mode in the previous class. So MN oblique MX bar is a signal that is used in order to differentiate between microprocessor 8086 operating in maximum mode or minimum mode. Then we have RD bar. So RD bar is an active low signal. So an active low signal at this pin shows that microprocessor is performing read operation either with memory or IO devices. So it is used in correlation or in conjunction with IO oblique M oblique IO in order to determine whether the read is being performed from memory or IO devices. Now clock. So clock, it provides timing to the processor for operations. We have learned in the previous class that 8086 has three operational frequency, quantifiably 5, 8, and 10 megahertz. So it provides the timing to the processor for operation. Its frequency is different for different versions. So 5 megahertz, 8 megahertz, and 10 megahertz. Now NMI. So NMI basically stands for non-maskable interrupt. So these are basically uncontrollable interrupts generated inside the microprocessor. So when NMI occurs, then an interrupt service routine is generated by reference to interrupt vector table, and the ISR is executed. Now likewise you have test. Now this pin basically shows the wait instruction. Whenever a low signal at this pin occurs, then the processing inside the processor continues. As and when this particular signal becomes high, the processor has to wait until unless the signal is not disabled. So test is used in order to show wait function or execution of wait instruction. Now likewise INTR. So INTR stands for interrupt request. So the processor, after each clock pulse, samples for the presence or check for the presence of INTR, and if the signal at this pin is found to be high, then the processor controls that interrupt internally, so or it manages the interrupt internally. So that is the significance of INTR. Now ready. Now ready, this signal is used by the peripheral or memory devices in order to notify the processor about the readiness for performing the next operation. So this is the significance of ready signal. So this signal is used by peripheral or memory devices in order to coordinate action with the microprocessor. Now, the next signal that we have is reset. So whenever the pin is enabled, then the processor is reset, and the other devices connected to the system by immediately terminating the recent task. So whenever this pin is enabled, then it resets the microprocessor and other devices connected to the system by immediately terminating the recent task. So that is the significance of the reset pin. Now we have INTA. So INTA stands for interrupt acknowledgement. So it is an interrupt acknowledgement pin. So whenever INTA request is generated, then the microprocessor generates an acknowledgement in order to acknowledge the receipt of the INTR request as a response to the interrupt. Now the next signal that we have is ALE. So ALE basically stands for address latch enable. So ALE is an abbreviation for address latch enable. So whenever address is present in the multiplex address data line, then microprocessor enables this pin. So this is done in order to inform the peripheral and the memory devices about a fetching of the data or instruction from the memory location specified. So that is the significance of ALE signal. The next signal that we have is DEN. So DEN basically stands for data enable. It is an active low signal. That means whenever a 0 is present at this pin, then the transceiver gets enabled and it separates the data from the multiplex address data line. So this is the way how the data will be perceived. Now DT oblique R bar. So this pin is used in order to show the direction of data transmission, whether the data is being transmitted or whether the data is being received. So this pin is used to show whether the data is getting transmitted or it's getting received by the microprocessor. So a high at this pin provides information regarding the transmission of data, whereas low in this pin indicates reception of data. Now you have M oblique IO bar as the next signal. So this pin indicates whether the processor is performing memory operation or IO operation. So whenever whether a microprocessor is performing operation with memory or IO devices. So whenever a high is present at this pin, it shows that the operation being carried out is through memory, whereas a low signal indicates operation is being performed through IO devices. So that is the significance of IO oblique M bar. Now the next signal that we have is WR. So it's an active low signal. So an active low signal at this pin indicates that the processor is performing write operation from either memory or IO devices. So depending upon whether we are interacting with IO device or memory, so WR basically refers to write operation being performed either on memory or IO devices. Now the next signal that we have is called as hold. Now, hold signal is used in order to coordinate the use of buses between the various devices and the microprocessor. So when an external device enables this pin, the processor stops accessing the bus immediately after the recent task gets over. Hold indicates that another master is requesting a local bus hold. So to be acknowledged, hold must be active high. The processor receives the hold request, receives the hold request, and then it issues a hold acknowledgement as an acknowledgement to the hold request, and it is done in the middle of the T1 clock cycle. Simultaneously with the issue of HLDA or the hold acknowledgement, the processor will float the local bus and the control signal, or it will relinquish the control of the local bus and the control lines. So after hold is detected as being low, the processor will lower the hold acknowledgement, and when the processor needs to run another cycle, it will gain the control of the local bus and the control lines. So this is the way how hold basically works. So hold is used in order to coordinate the use of the buses amidst the interacting devices. Now hold acknowledgement. So hold acknowledgement, this pin is used as a response pin for hold request. As we have already learned, it's an acknowledgement for the hold signal. So once request for accessing the bus is provided by external entity, then the microprocessor acknowledges the device that is requesting for the use of the buses, which will be considered once it gets over by the current operation. So once the current operation is over, it will relinquish the use of buses. So that is the purpose of hold and hold acknowledgement. So these are two important signals we need to understand. Now some of the signals that are defined for maximum mode. So we have S0, S1 and S2. Now S0, S1 and S2, these are basically three status pins and are active low. This means that if the status at the three pins is 0, then it shows that multiple interrupts to be handled in case of maximum mode. So here this is the way how the interpretation is done. Now 000 basically refers to interrupt acknowledgement. 001 refers to read IO port. 010 refers to write IO port. 011 refers to halt. 100 refers to code access. 101 refers to read memory. 110 refers to write memory, and 111 refers to passive state. So these are the possible combinations of S2, S1 and S0 representing different characteristics. Now let us move on to the next signal, that is QS0 and QS1. Now these two pin indicates the status of the 6-byte prefetch queue present in the architecture of 8086 microprocessor. So we have learned about the importance of prefetch queue. So it is used in order to store prefetch sequence of bytes that are to be executed next by the execution unit. So it is used in order to enhance the performance of the microprocessor. So QS0 and QS1 are used in order to indicate the status of 6-byte prefetch queue present in the 8086 architecture. So 00 basically refers to no operation. 01 basically refers to first byte of the opcode from queue. 10 refers to empty the queue, and 11 basically refers to subsequent byte from the queue. So these are the two signals that are used in order to indicate the status of the 6-byte prefetch queue. Now the next signal that we have is called as lock. Now lock, this pin is involved in maximum mode of operation. So basically, when a single processor is accessing the buses and, and peripherals, then it locks the resources by being used by it, so that no other entity can access it until the recent processor frees it. So lock is used in order to lock the resources that are being used by the processor, resources that are peripheral buses and peripherals that are being used by the processor under consideration. So it's basically used in maximum mode in order to ensure that uh, the resources that are available are properly used. Now, request grant. So RQGT0, RQGT1, request grant. So due to the involvement of multiple processors, this pin indicates the request and grant permission for accessing the buses, memory, and peripherals. So that is the purpose of request and grant signals. So in this particular class, we have learned about uh, the pin diagram of 8086 microprocessor. We have seen that 8086 microprocessor has 40 odd pins sequenced from 1 to 40, and we have also discussed the various signals that are across the different pins of 8086 microprocessor. We have also seen the difference in the signals that are there associated with the 8086 microprocessor in case of maximum mode and minimum mode. Then we went through each of these signals and try to understand the significance of all of the signals that are there associated with the 8086 microprocessor. So, I would like to conclude the class here. Thank you very much and have a very nice day.